So I'd like to also thank the organizers for this meeting. I'm here the second time after Rohini passed. I was here already in November, and it was also very sad then, and it still is. But it's great to have this memorial conference to celebrate her and her achievements and her life in general. So in that life, she visited the Netherlands actually quite a few times. I'd like to tell you a little bit about the story behind that. So in some sense, even though we don't quite look alike, we were siblings. We were both students of Jack Smith at the Institute for Theoretical Physics in Stony Brook. We didn't overlap, but growing up in the same environment, the same family there, which is a family of great physics stimulation and great social isolation in this village on Long Island, that sort of creates, some of you here know, a bit of a special feeling, and we certainly share that. And with that, and also her personality, it was only natural that we became friends early in 2000s. So what I'd like to do here is discuss a few items of physics, sketch them, what we talked about, although we did not write paper together, and then a few things on Rohini's role in and for the Netherlands. So Rohini was, as we all know, extremely curious, widely interested. I can't think of any topic she found uninteresting. Right? I think this is really it was never difficult to find topics, physics or otherwise, for discussion. And as I said, we never managed to publish together, but we had plenty of physics conversations on, as Manuel's reminded me, resolved photons, but also these topics here. And in recent years as well, since I'm a member of the CERN Council and also involved in setting the strategy of CERN, the future of particle physics in India, the future of CERN, and how they are connected. I think those have been very interesting and very valuable conversations also for me. So let me bring up a few physics topics, a bit out of a shoebox I found in the attic, but maybe it's still good to go over some of these items. So one topic that we discussed quite a bit is single top production in hadron colliders. As you know, these are the single top production diagrams. The S channel, the fat line, is the top quark. The T channel, and this is WT production. And you can do a lot of stuff with single top, as we already saw, because it's sensitive to new physics in different channels in different ways. And it tests, of course, electroweak production of the top, and particularly that chiral structure. So it's very special that the top decays in this two-stage process, first to a W, then to leptons, because and here are some drawings of choosing the specific angles. Here is the angle between the top quark spin and the emerging charged lepton. That's the most important one. Because if you really look at this decay, spin up polarized to charged lepton to spin down polarized, all that changes is a sign here. In fact, this is the correlation thing. It's a perfect 100% correlation, which you don't have after one decay, but you do have after the second decay. That's the power of interference. So that really gives the charged lepton a handle on the top quark spin, and that allows you to test lots of stuff. So that's the beautiful theory. More realistically, at the time, we had just implemented single top production in the MC8 NLO Monte Carlo framework, together with Friccione and a student of mine, and Brian Weber. And we would like to see how much of that translates then to real collider, or at least semi-real collider circumstances with cuts and parton showers. And in fact, these are just Tevatron plots. Similar plots have been made for LHC. That depending on what your quantization axis is, either the beam direction or the hardest non-B-jet, what you're trying to imitate is the down type quark that comes out. That comes out here, because that correlates via the top most strongly with the charged lepton. And this, as you can see here, the T channel has the strongest correlation. So it really showed that these theoretical correlations actually also can show themselves in more realistic setups, and that's now being used a lot. Another topic, again single top, is to look at the sensitivity of the single top production to beyond the standard model physics in a bit more detail, I did this work together with Laenen and two Atlas physicists. But we had a lot of discussions with Rohini at the time. Just to briefly remind you, in SMEFT, you extend the standard model with dimension 6 operators, each with a coefficient, and you limit yourself typically to 6 because 8 is too hard. It's also presumably smaller, and the idea is make predictions with this extended theory and confront with data and see if you can determine what the size of these seeds are. If they're non-zero, that's interesting. So what we did is we did not include dimension 8 operators, but used the square of dimension 6 as a sort of error estimate. The advantage of this whole approach is you don't assume new particles, you assume new interactions, but you do keep the same symmetry group. Downside is there's still a bit too many dimension 6 operators. This is the number, just one short of 2500. But for the reason we did it for this reaction is that in this case only 3 operators effectively matter. So the goal in this project was to simulate single top production with 3 relevant operators only. I'll mention them in a second, and study their effects in decays, other subtleties, and narrow width approximation, sensitivity of cross sections to the new operators, and even look for CP violation in single top. So these are the 3 operators. This is a Higgs heavy quark doublet combination, a TW operator, which even has a non-Hermitian part, and a 4 quark operator. And we see what is their effect in this simulation, particularly in the MADGRAPH 5 AMC NLO simulation. So these new operators lead to new Feynman diagrams. You can see what is their effect. Well, at the parton level, you sort of see the left-handed coupling is extended by this term, and there is even a new right-handed coupling. The effect at the amplitude level is linear, but once you square the amplitude, you get also quadratic terms here for cross sections, and you can see what the effect of all these extra insertions are. This is at the parton level, where we have the 3 operators with these known functions of the angle theta, the angle between the bottom and the top here. And you see there's 3 different curves here, and they have 3 different, this is the standard model one, and they have 3 different effects. The question is then how much of this does remain once you do all the proper simulation and inclusion in a full parton level framework. This is a table I don't invite you to read, other than maybe to accept my assurance that the effect, particularly of the 4 Fermi operator, can be very large. And it's a signal that you better include this, and we include them here as strength 1, which is also a bit much, but just to see what the sensitivity is. At the level of distributions, you also see, particularly here, the 4 Fermi operator at large PT for the top has a large effect. For the rapidity of the top, it is less so. So these are some of the studies we were doing. In earlier talks it came up maybe not for this reaction, but how do you simulate? The easiest is to make a stable top and let the rest decay via other programs. The most correct would be to not factorize at all, but simulate the full final state. All of this at next to leading order. That last thing, this full chain, is too computationally sensitive, so we took this intermediate approach where we simulated the W bottom J final state and decayed the rest via mad spin. Actually, at the same time, roughly the same time, I was discussing a lot with Rohini, because they had just, together with Ritesh and others here, had written a paper showing that there is a certain insensitivity to new physics in the WT mode in this, so we had a lot of interesting discussions on this. There's also a subtlety on the top width, so not just the production, but also the width changes to these new operators, and once you include all that, and be very careful in the narrow width approximation, I'll go a bit fast here. It just shows you have to be a bit careful what the sensitivity of your prediction is as a function of the Wilson coefficient for that extra operator. And at next to leading order, again, now next to leading order in QCD, you see again still for the PT of the top still sizable contributions. Finally, in this topic, the CP violation operator, the WT operator here, has indeed a small sensitivity, depending on the strength in front, of course, to CP violating effects. And it's not impossible. In fact, we got a project approved in the Netherlands to look for these things in Atlas, unfortunately. And we discussed with Rohini a lot what the best access is to show up such CP violating effects. In the end, it's not so sensitive, Atlas, unfortunately. So, but perhaps more is possible there. And at present, the status is that this is 3 operators now. People are much more advanced, and they use a whole bunch of operators. One of the nice things is these type of plots. These are called, I've heard them called spider plots. Have you seen them? These are, on every axis is a Wilson coefficient for all these operators, and you sort of, 0 is no new physics, and for each operator you can see how much will it be constrained by new data. So it's a very nice way of, instead of having all these bars, this is a much nicer way to show it. A final little topic, just a few slides on supersymmetry. This was, of course, after all, one of her passions. How often do you make supersymmetric particles? And we included here in this extensive collaboration also students of mine that she had and others who had that she had been working with. And all we did there is to include QCD corrections to all orders in perturbation theory using threshold corrections here in the exponent to make the production of colored supersymmetric particles as precise as possible. Plan for success, assume you will measure them, and then also try to see what is the best possible prediction for them. Here are the threshold logarithms. So the logarithms get large when S is close to Q squared, when the threshold log is large. And that's what you have to sum to all orders in order to have a well-predicted theory. In this business, by the way, it's always worthwhile reminding threshold can mean different things to different people. The basic threshold is just 4m squared if you have a particle of mass m. But if you make a particle at a certain pt, the threshold is larger. And if you also include rapidity, it's still larger. So you can do all these things and still have pt and rapidity. And then we, in fact, put the whole thing, this whole resummation picture, including all the initial state radiation, final state exchanges, all of that together in a code, and recently got updated to version 2.0. It's much used by Atlas and CMS. Okay, that's so much for the physics. Now a few words on Rohini's role in the Netherlands. So the first time she came to the Netherlands, which she came to often, was often combined with a visit to Annecy. I think that's usually what she said, that she on her way from Annecy or to Annecy. First longer time is when I was able to apply with her for an Utrecht Asia visiting professorship in 2011, and she came for 6 months, taught a supersymmetry BSM course with 20 very enthusiastic students, many of which also stayed friends years afterwards. But also she was really a friend to the whole institute, including even Gerard het Hoofd and Bernard de Wit. So here you see her in Utrecht, not in 2011, this was later. And she wanted to see this building, and you can't read it, but it's called the Caroline Bleecker building. Caroline Bleecker was a really remarkable woman. She was a technology entrepreneur in the 1930s. She started a company in the 1930s, just before the Second World War, in optics, and carried it through the war and until after the war, and was really quite far ahead of her time. And so Rohini was very fascinated to learn about her story. In 2018, we invited her as a visiting professor at the University of Amsterdam, and she stayed also there some months, gave a lecture course in Higgs physics, again attracting many students. A particular highlight was when we organized a big faculty-wide colloquium on women in science, the story from India, with a forum discussion afterwards, and that was, it completely filled our largest auditorium and was a great success. There's also lots of younger female faculty there from all different departments, chemistry, physics, and others, and she was a magnet for them. She was extremely inspiring, and she met with many of them on that visit and other visits later. This is a scene in near a farm. You can sort of see the typical Dutch flat landscape. And this is at dinner with my son, who has my height. Thankfully, not my hair. So, not yet. So, but Rohini perhaps felt most at home at NIKHEF, also in Amsterdam, across the street from the university. And she came many times, and all of us were always very happy when she visited. Her last major contribution to NIKHEF and the Netherlands was when she was in the evaluation panel of NIKHEF in 2023. We had discussions then as well, particularly after, but she had a very clear vision of what was valuable to do for the Netherlands and for NIKHEF, which had a bit of a tendency perhaps to go too much to astroparticle physics. And she gave a very good plea to not forget the focus on collider physics as something that is important to do for the future as well. And she and I certainly agreed on that, and we had some very good exchanges of views there. But she was often part of also social events in our group, so it was always a fun. She was a member of many theory groups, in fact, in the world, as we've been hearing, but certainly also of ours. So my colleagues and I in the Netherlands will really always be grateful for what she has done for us. And we not just remember what she has done, but also with great fondness how she did it, with her energy and warmth. And we will always remember that and appreciate for what she did. Thanks.